Greetings. My name is Mr. Les Rexedler. This webinar is about HVDC life assessment and extension, and it's from the Manitoba HVDC Research Center, which is a division of Manitoba Hydro International. If you have any questions, I'd like you to type them in the area on the right-hand side, and at the end of the meeting, we'll answer as many of those as we can. Thanks very much. Okay, this webinar is going to be about the following topics: introduction and background, documentation and records, root cause analysis, assessment team and preparation, performing the assessment, HVDC cost analysis, lifetime of components, equipment analysis, environmental and regulatory, techno-economic analysis, conclusion, and then questions. Introduction. This webinar is based on 40 years of experience in the HVDC industry and associated areas of operations, maintenance, performance, failure analysis, design, and consulting. I've also actively participated in condition assessments of 11 HVDC converter systems for all of or parts thereof of the HVDC converter stations, not the transmission lines. This experience is based on the Nelson River Bipole 1, plus minus 463.5 kV, 1854 megawatts, commissioned in 1973 to 76, because it was the number of groups in series. And my experience started in December of 1975 till 2009, when I left Manitoba Hydro and joined the Manitoba Hydro International, the Research Center. Also, at the same time, there's Nelson River Bipole 2, plus or minus 500 kV, 2,000 megawatts, commissioned between 1978 and 1985, and again, the same experience time. The third major project was Cabarabassa, Mozambique, and it's plus minus 533 kV, 1,800 amps, commissioned in 1976, and I was involved from January of 2007, and it's still ongoing. I was also involved in 8 other HVDC projects as part of a team or as an individual. And I also was involved in the HVDC users meetings from approximately 1980. The next section is documentation and records. This is a good thing to look at, probably even more so when you're starting an HVDC link or even thinking about one, as to how the records will be used to do failure analysis and life assessment down the road. It's kind of hard to think of life assessment when you're first starting a project, but it is really important to actually look at this, because the information that you have available will depending on what you collect over the years. So you need to decide at the beginning what level of detail to retain, as there are costs associated with this. The greater the detail, the more significant the benefits, but also the more significant the costs. And the other thing is you need to have a system on how to retrieve the information in the forms required for the maintenance, performance analysis, and life assessment. And I stress the word retrieve, because most filing systems are designed to file things and not necessarily are designed to extract the information in the format that is the easiest and most complete. And so you have to think about how to retrieve the information, not necessarily how to file it. You also need to consider root cause analysis. And this sounds funny at this stage in the game for doing an assessment, but root cause analysis really hones in on the actual root cause of the failure or problem or condition. And many times, if you don't do a root cause analysis, you wind up actually trying to fix the wrong problem, and what you don't get is any improvement in performance and availability and reliability. Manitoba Hydro uses a software called ProAct by Meridian to help us with this process, but it is a manual process, and there are lots of other softwares out there available. We're not trying to market this one in any way, shape, or form. You should basically look at whichever one works best for you. Root cause analysis is very important to drill down to the most detailed level to improve performance or sustain performance. And so this is very useful throughout the entire project life. It is really even more important at the end of the project to do the analysis, but to keep and improve the performance throughout the project is going to be very beneficial and worth generally a lot of money throughout the entire project. A higher level of records with less detail affects the life assessment and the cost of extension and replacement. But many times, because documentation hasn't been done early enough in the game, or documentation is insufficient or hard to find, that's all that is available. Numbers of decisions have unfortunately thus resulted in poor decisions, because this was not done at a detailed level, where people have spent a lot of money trying to fix the problem and not getting a corresponding improvement in performance. And so this can be very frustrating, very costly, and not a good reputation for the actual link itself. The assessment team. The assessment team usually requires a number of team members with a diverse background of skills and expertise, and also experience. You can't, unfortunately, replace experience. Some of the areas that are quite useful, and there may be others that you might think of, is converter transformers and reactors, HVDC controls and protections, and also communications, thyristor valves and cooling systems, the DC switchyard, the AC switchyard, and in a lot of cases you may also want to have some financial people involved in the process. Assessment preparation. It's best to prepare a list of information to ask for and review ahead of time, and try to get as much information as possible. This simplifies the task once you get to site, in that you have less of a task to try and get information from site. Likely, though, not all the requested information will be available. So you ask for as much as you can get. The reality is it's very unlikely that you'll get everything that you requested. A site visit, if it's not your own company, well, even if it's your own company, should be mandatory. Looking at the equipment is a really good idea. You can get a really good idea of the actual condition of the equipment at that point in time. A minimum of about 5 years of information at a detail level should be reviewed. This may require some work on the part of the utility that you're dealing with, and on your part itself to actually generate that information. And so sometimes part of the assessment is actually to generate the information that you need to do the review. And so that can be a fairly time-consuming process. If you have the documentation at the beginning, this process is a lot less onerous. Failure reports that are kept in the system, if they're available, can be very valuable, especially with high-cost items such as transformers and thyristor valves and equipment like that. They can give you a lot of information as to possible design deficiencies and/or the actual condition of the equipment itself, especially if they have taken a paper analysis from the transformers as an example. The next is assessment preparation is to meet with the client to get a clear understanding of their expectations. Now, the client may be people within your own organization or a utility. So client in this case is used in a very generic term. And it's really to understand the expectations that are going to come out of the analysis, information available, and of course the deliverables that you're going to have to deliver as part of this process. You really need to understand the process and approvals of the client so that the assessment information is in a format that's required for company management and lenders. So lenders might be banks and things like that. They may have different requirements. They may have financial models that you need to fit things into. Also, your own company has probably a process of going through to support justifying the project, whichever it is, for refurbishment of parts or even a major portion of the HVDC scheme. Again, get as much information as possible from the client or from other people in your organization before the site visit. And it is very likely that a second visit may be necessary to get additional information and or present the final report. So generally, a lot of times when you get back, you'll find that there is additional information that would be beneficial or useful, or additional testing that may be required to come to a conclusion as to which way to go. And of course, usually the client, be it within your own company or the management in your company or an outside client, will generally want you to present a final report and of course ask a bunch of questions about how it was arrived at. The next one is actually performing the assessment. Performing the assessment is in the site visit in general is you take a lot of pictures of the equipment, nameplate, and write a lot of notes basically throughout the whole process. Keep a daily log. Taking lots of pictures is really important because when you get back, you're going to ask. Lots of times you're going to be reviewing the information. You'll say, well, "What about this piece of equipment?" or "What about that?" And if you have lots of pictures, it's likely that you may actually have something in there, and that you don't have to request that information or go back and collect it the second time around. So lots of pictures, lots of notes is very, very important. Another one of probably the most important part is to interview your operations and maintenance staff, and with a focus on outages and cost of outages, if that's known, if they know what the cost of outages are. You find in most instances, most of the problems are not documented well. And by talking to the operations and maintenance staff, you get a better idea of problems that haven't been well documented over the years. You have to be careful with that information because it is word of mouth, and it is sometimes not as accurate as you would like it to be. So you have to be very careful when you ask the questions of the staff to kind of verify it as much as possible what they're saying with other staff in the group. The The next part is to differentiate between one-time failures and systemic or design failures. One-time failures or quality failures are things that can be usually handled and fixed at a relatively low cost, whereas we get into systemic or design problems, they usually affect, and especially in the case of HVDC, they usually affect all the similar equipment. So if you have a transformer design problem, as an example, you probably have transformer design problems with all of your converter transformers. So it really has a huge impact because all the equipment is generally built at the same time, or at least from similar designs. So obtain as much information as required, especially failure reports. I've kind of touched on this before. And again, one of the most expensive pieces of equipment is the transformers. So this is really important in that area. Again, performing the assessment, it's good to look for trends over a long period of time and be careful with information that is only short-term or is only available short-term. An example of this is thyristor failures. Can cite an example that we had in our own company where the thyristor failures started to increase, and over the short term, a period of 2 to 3 years, the increase seemed very rapid. However, by the time we got to the 4th year, the thyristor failure rate had returned to normal, and we analyzed it in detail. The failure rates were still well within the guaranteed yearly rate of failures. So there was a needless panic to look at replacing the thyristor valves when, you know, a short-term look at the failure rate would indicate that you had a serious problem. So be careful of these things when you have only a limited amount of data, and especially a short time frame of data. You also have to consider critical spares and usability of the spares. Sometimes critical spares are not available, such as DC bushings, or in some cases the DC bushings are not in good condition. Sometimes even spare transformers have been in service, have been gassing and been sitting on the pad there, sort of as an emergency spare, but it's not really in good condition. And reviewing that information shows basically that this spare is not really a good long-term spare to be counted on in the long run, and should be part of the assessment because, of course, you will be replacing these as part of the process if you're going to replace the converter transformers. You need to develop an evaluation criteria for each piece of equipment or system, and I say major equipment only. I think developing an evaluation criteria is very important because you want to consider the most important items have the highest weighting, and minor items would have only a minor weighting, so that you can determine when, in fact, it gets to the point where you have a significant amount of major items that are not in good condition. And you have to decide what is important with respect to this evaluation criteria. Some examples are age, spares available, obsolescence, and skills of the staff to maintain. So these are some of the items that maybe don't really jump out at you at first. They're part of the equipment as well. If you don't have the adequate skills to maintain, it may be that you have to replace the equipment, or maybe you have to do some training as part of the refurbishment. So there's areas that you think of that, or may not think of it as part of the assessment. Look at equipment with good performance as well to see if there could be a major drop-off down the road. A lot of times assessments focus only on equipment that is having problems or equipment that is near the end of life, and basically you have to look at other equipment that may not survive the refurbishment process. Like, for example, cooling systems maybe have a 25-year life and they're okay now, but as far as the refurbishment is concerned, will they last another 15 to 20 years? And so you may decide at that point in time to replace them earlier, or to at least schedule a replacement down the road when they start to give you problems. But at least it should be part of the assessment process. Okay, the next one is the cost of HVDC, and this is a typical pie chart. The numbers and percentages would probably change for every DC link in the world, but it gives you an idea of the relative costs, and it gives you an idea of what we're going to be going into here. The two areas that we're going to go into are the ones with the two highest percentages, which is converter transformers and thyristor valves. And when you consider that each one of these has aspects of civil works, freight and insurance, engineering, erection and commissioning, you can see that they together probably make up over 50% of the cost of a converter station. And that doesn't mean that all this other equipment needs to be ignored, but I think if you find out that the converter transformers and the thyristor valves have to be controlled, it's more than likely that you have to be replaced. It's more than likely that you have a serious refurbishment problem and or a replacement problem. Generally speaking, the controls and the valves go together as well. And a lot of people will replace the controls with the valves because they go together as a package, and it is generally recommended, but it isn't always done. Sometimes the controls are replaced without replacing the valves, and sometimes the reverse as well. So the converter transformers and valves have the largest cost implications, and thus the focus will be on these first. Costs will vary from project to project, so these are only representative. If you add in, okay, I've already gone through this, so we'll just continue on. This is a picture of a bipole 2 converter transformer from the Nelson River system at the Dorsey converter station. One of the things about it, it's designed to go in service fairly quickly, in that the deluge system is connected to the transformer itself. The coolers are also connected to the transformer itself, so that it is basically a unit by itself. The AC bushings are a different color than the DC bushings, so you can very readily identify different pieces of equipment, and sometimes this is useful when you're doing or replacing equipment, that if you make it a different color, you can tell immediately that this bushing has been replaced and this bushing hasn't been replaced, as an example. So there's a case where if you're doing refurbishment, sometimes the use of color can be very useful in determining, just at a glance, when you're looking at this equipment, whether or not it has been replaced or not. And originally these coolers were separate, and originally the deluge system was separate, but to speed up the replacement process, we went to unitizing this into one unit, so that it can very be easily used and very easily put in service. This is a picture of the bipole 2 in the Dorsey converter station. The converter transformers, again, in this picture and the previous picture, are of an older style, because this one went in service like in 1978 to 85, and so you have the transformers are separate from the actual wall bushings. Whereas in a new DC system, the transformer bushings would go through the wall into the building itself, and this shows you where the cooler is actually separate, and the deluge system is separate from both. So it shows you a bit of the old style design. And some of the replacements and refurbishments have been dramatically changed in design as part of the refurbishment and spares. So with the converter transformers themselves, it's necessary to separate those that can affect the usable life of the transformer versus those that can be readily and inexpensively replaced. So ones that can explicitly affect the life of a transformer is the core, windings, and the DC bushings. This may be a surprise to many people, why we would include DC bushings. The DC bushings are very unique in that they are really part of the insulation structure of the transformer itself, and therefore they must be replaced with the exact make and model if the DC voltage is above 150 kV. In a lot of cases, replacements may not be readily available, or they might be very expensive. So So in a lot of cases we found in our system and in many other systems in the world, replacements are not available at all. So that it can be a huge problem with respect to trying to extend the life of a piece of equipment. And I'll go into a bit more about that later. AC bushings, tap changer controls, and the actual converter transformer controls are usually not considered a driver. And what I mean is that they would not drive you to do a replacement itself. They usually, if you're going to do some refurbishment to the transformers, these would be sort of an add-on to that. I mean, they may get to the point where they have to be done, but usually if you're going to be doing other stuff, these would be added on. There is possibility that you may have to replace, you know, all the AC bushings or tap changers, refurbish them by themselves, but it's very rare. You may also need to consider the protection, the cabling. A lot of times if the transformer is, say, 30 years old, the cabling is also 30 years old, and if you're going to be doing some refurbishment, it's very likely that you're going to have to also replace some of the cabling. Maybe some of even the concrete needs to be refurbished that it's sitting on. Maybe there wasn't oil spill containment, maybe there wasn't fire protection originally. These things would have to be looked at, and you may want to consider including them in any refurbishment. And you also need to consider losses and original design flaws. So especially if you're getting refurbishment or you're getting additional spares purchased, you can get transformers with a lot lower losses. And of course, you want to design out any design flaws that were in the old equipment. Lifetimes of components, basically. So what I'm going to give you here is the lifetime of the components for the converter transformers. Lifetime does not mean necessarily end of life for a piece of equipment, because every piece of equipment isn't necessarily going to live up to the average lifetime. But what it means is that this should be reviewed prior to this, and usually we choose a figure about, say, 5 years before that to see if there's remaining life or not. And that's only if there hasn't been a lot of problems up till then. If a piece of equipment is causing you a lot of problems before that, it's very likely that you've already done a review or should have been doing a review of them. So this is just a general thing that if you haven't had any major problems up till then, maybe it's time to look at this for the AC bushing, say in the 20-year period of time, to see whether or not they are going to last to the 40 years. As you can see from the numbers here, the converter transformers have a life of somewhere between 35 and 40 years, and maybe in some cases beyond. However, the AC bushings likely do not have the same lifetime. More probably in the neighborhood of 20 to 25 years. And the thing about the AC bushings in particular is if they do fail, I mean, there's a good possibility because of the high fault levels that you may have a tank rupture and fire and things like that. 90% of fires in transformers are caused by bushings. So sometimes maybe the better thing from a fire protection point of view would be to replace the bushing and remove the causes of fire than worrying about having a lot of fire protection, but you'll probably want the fire protection anyway. DC bushings have about 20% more insulation than an AC bushing. They tend to last longer. 30 years is not uncommon, and some last beyond that as well. The tap changer itself has a life of about 350,000 operations. It may be slightly more for some types of tap changers, or about 30 years. The thing is with DC links, tap change operations are generally fairly high. In our system, we average between about 6,000 and 12,000 operations per year. But there are some DC links that have up to 30,000 operations per year. So if you look at that 350,000 operations, in somewhere around 12 years, 13 years, you're already at the life of the tap changer itself. Coolers also have a life of about 30 years. Some other coolers may be a little bit less in the system. Transformer coolers tend to be a little bit better built. And the controls also should have basically around the 30-year life itself. As far as determining the core and coils, one of the easier ways to try and get a handle on the assessment of the condition of them is by dissolved gas analysis, or DGA. There's a number of different ways this can be done by Rogers ratios, Duval's triangle, or Doenberg numbers. There's a whole host of different ways that you can look at this. There's an IEC standard that helps you with the analysis. There's an IEEE standard that helps you with the analysis. Many manufacturers will also have their own guidelines or DGA results specific to their converter transformers. I know ABB does, as an example. So lots of times, if that is available to you to do the assessment, it's probably best to use the ones that match closest to the equipment that you're trying to analyze. And large companies may also have their own DGA results and guidelines based on their own experience and years of testing and things like that. It is also important to know which method is being used by some of the test instruments that might be used at site for generating some of these records, so that you know which method was used, if it was Rogers ratio or Duval's triangle, or which. Example might be, say, a Morgan Schaefer site test DGA. Again, the most important part of doing this analysis is trending. Okay, trending gives you, and you want a minimum of at least three separate readings to see whether the problem is increasing, decreasing, or stable. And of course, it will vary somewhat with loading, so you have to take that into consideration as well. But if you have a bad reading, it can very easily show in a trend, whereas if you only have a couple of points, a bad reading can give you a very bad result as far as trying to do the analysis is concerned. Analysis can also be very difficult, as there may be multiple problems. So, in other words, there may be actually more than one problem going on inside the transformer itself, and this can be very confusing to try and determine what's actually going on inside the unit itself. So one of the other things that's quite useful is furan analysis, which is the degree of depolymerization, and it usually is units from 200 to 100, and this is as per the IEC standard 60450. And the 2-furfural correlation with cellulose degradation gives you a fairly good idea of the actual indication of the paper or cellulose inside the transformer, which is the windings, and is the most likely source of failure, but not necessarily. Wherever you have information, it's really useful if you can correlate this with other information. And one might be with the furan analysis would be the CO2 to CO ratio between 3 and 10. Of course, other people use different numbers. This is a number that's used commonly by ABB, and so I've decided to use this one here. But other numbers can be used as well in this regard. Whatever number you're decided to use in the analysis is what you should use. But again, correlation of results, trying to get more than one indicator that shows the problem in the same problem, is really, really useful. If you only have one indication, it may or may not be as accurate as you think it is. Another thing is contaminants can really influence the results. Contaminants can occur for many reasons. Sometimes top-up oil with bad oil has been used. In other cases, there's been materials used in some refurbishment process throughout, and it's caused, say, a very high CO2 to CO ratio. And yet, when you do the furan analysis, there's no correlation to the furan analysis, so you know that you have a contaminant rather than a paper problem. And again, trending is very important. So if you get these analysis over a period of time, it's a lot more useful than just having 1 or 2 points. Other information that's useful is transformer failure reports, discussions with site staff, operators and maintenance. If you also have the unique opportunity to talk to the designers of the transformers themselves, You may also get significant information. In some cases this is possible, but it's fairly rare. And again, a visit to site to actually see the transformers and see what other conditions they're in, such as oil leaks and other types of issues, equipment that might be missing or whatever. And of course any design issues is known. Like I said, if you have a chance to talk to the designers, or if there's design reports or failure reports, they would be very, very useful. AC and DC bushings, measurement of the C1, C2 and dissipation tractor, of course with trending again, is very important. This is a screening process only though. If the screening process is okay, it's showing that there's not necessarily a problem, but that doesn't mean that they still will not fail due to dielectric voltage failures. So another example is oil sampling. If you have an oil-filled bushing, you can do an oil sample on it. Some of the bushings though are nitrogen capped, and of course you'll have to replace that nitrogen cap when you're finished. So a detailed procedure is really, really important on how to do that. And of course there's a huge risk of contamination, specifically with moisture, depending on when you open the bushings to get the actual sampling. AC bushings, dielectric tests on 2 bushings, and again AC ones are very important because a failure can rupture the tank. We had a transformer going back into a factory for some repairs. We did some dielectric tests after about 20 years on the AC bushings. We were testing 3 bushings. We tested the first one, it failed at the arrestor pickup level at 75% of the full level of the BIL of the bushing, and the next one also failed at the same level. So the arrestor really wasn't protecting the bushings anymore. So we didn't test the 3rd bushing. We decided at that point in time that replacing the bushings was a much better option. So even though they had tested good with the C1, C2 and dissipation factor, that doesn't necessarily mean that the bushing will withstand the dielectric tests. So the other one is more of the screening test to say that if it shows bad, you should replace it or do something about it. But that doesn't necessarily mean that the bushings are actually good. DC bushings are the same. Again, dielectric tests on 2 of the bushings should be done. The problem with DC bushing is sometimes you get to the point where there's there's not enough spares available to do the test. And of course, it's only if the bushings are only 150 kV. And of course, bushing obsolescence, sometimes you cannot get replacement bushings anywhere from anybody. And you have to actually replace more than just the bushing. So in this case, like DC bushings, you may need to replace the DC barriers, DC leads, and new RIP bushings because you can't get the old bushings. This actually happened in Cabora Bassa, where they could no longer get the bushings, they could no longer be repaired by the supplier, and new ones were not available. Initially the supplier tried to put in a bushing that was just an RIP bushing without replacing the leads and the barriers, and within about 4 hours the bushing failed. And eventually they did go and do a finite element analysis and determine that the leads and barriers had to be replaced as well as new bushings. And then that's been quite successful. It is a costly process, but shipping transformers or the replacement of transformers is very costly. Shipping them to places like Mozambique is extremely costly as well. This is still a very economic option. This is a drawing of a DC bushing barrier, and it shows you a bit about the alignment of the barrier with the condenser foils inside the bushing, and you can see how they line up, and that's important, but that's not the only thing that's important. In DC as well, the voltage withstand capability of the different materials is different. So for example, oil does not support very much DC voltage, so you have to have paper involved, whereas an AC, oil will support a huge amount of DC voltage. So if you're looking at these things and comparing them, As an example, if you take out an oil-filled bushing and replace it with an RIP bushing, the stresses are completely different on an RIP bushing than it would be for an old oil-filled bushing, as an example. So you have to be very careful when you replace these DC bushings that you ensure that there's a finite element modeling done of the entire insulation system, the DC barrier and the DC bushing, to ensure that it's compatible. Decision criteria, number and weighting. So there's age, DGA results, Furin analysis, of course, DC bushings, health and spares, design problems, failures, failure reports, and other things may be site-specific, like I said, huge transport costs for very remote locations, or things that you may have to consider. And there might be other items that are specific to a particular HVDC line. This is a picture of a tap changer. It's at the Cabarabasa link, and it shows the diverter switch in the vessel on top, which is in this vessel here, and that's the one that does the actual switching of the current and the arcing. And then there's a selector switch at the bottom here, and we'll get a bit more into the life of these as we go on. So, remaining items, if transformer is retained, that has to be looked at. Tap changer, life of about 30 years or 350,000 operations. Basically, I said normal in our company is 6,000 to 12,000 operations per year. The cooler is you can do efficiency tests of how much actually temperature drop there is across the cooler and the flow rate to get an idea how efficient the coolers are. The control cabinets, of course, you can look at them as far as parts are available, refurbishments possible, and in many cases the power, in our case 600 volts, and the control voltages are in the same control cabinet, and we like to try to separate the 600 volts into a separate cabinet. So if you're actually doing any refurbishment of the control cabinet, this is something you may want to consider. Also, some of the new standards have new layouts for control cabinets, and you may want to have a look at those and see if they would be applicable to your particular refurbishment or not. There's a possibility as part of the refurbishment to replace the oil temperature indicator, the winding temperature indicator, and some of the pressure relief devices with better versions that are electronic, a little more accurate and a little more reliable in a lot of instances. And other problems and concerns are oil leaks and, of course, the cabling and things like that that you may want to consider. Thyristor valves. This is a picture of our Bipole 2 valve hall, and this is a picture of of course, the wall bushings coming through the wall, and we have in here a one that is a different color, and so you can tell right away that it's been replaced. And this is a SF6 filled 500 kV with silicon rubber bushing sheds on it. So this was placed in service in approximately 1989 and has been in good service ever since. So one of the biggest things in HVDC has been the transition to silicon rubber and silicon rubber RTV, and it results basically in higher voltage withstand capabilities, lighter, safer from a safety point of view, and stronger, surprisingly, than a DC bushing, porcelain DC bushing, based on the testing that we have done. So Thyristor valves are custom equipment. They're only available generally from the supplier, but surprisingly, lots of replacement parts aren't. So items to consider are the thyristors, the cooling pipes, reactor modules, and the damping circuits. Other items to consider are the valve-based electronics, including the fiber optics, the valve arrestor, support insulators, and also the fire design of the thyristor valve itself. Refurbishment. Even though this is custom equipment, most parts can be sourced if the general condition of other parts in the valve are okay. I suspect that there are some suppliers that don't like to hear that, but this is reality. One example is one utility replaced the cooling pipes from a supplier for about $6 million Canadian, whereas to replace the thyristor valves, which was the other option, which many people were pushing for, was $200 million Canadian at that time. Now, just the interest on $200 million is about $10 million a year, $12 million a year. So the payback to actually do the cooling pipe replacement was really half a year. And so far, this has extended the life of the equipment by 18 years and counting. So refurbishment, in some instances, can be very economic and can really extend the life of the equipment. Parts may be available from the OEM, and in some cases they're not. In other cases, they're available from other suppliers, but usually some form of engineering is required. So, for instance, we did run out of spare reactor modules in our Bipole 2, and we went back to the supplier. They could no longer make the original reactor modules. These are the ones that are in the valve itself. They're a current limited reactor, and they did a custom design for us, which we paid for, and then we got some 25 reactor modules on a cost plus basis. So again, it was less expensive than replacing the valves themselves. So a part of the assessment, though, needs to be the risk versus the cost saving. Lots of times, the risk of not having the equipment available can be very expensive, and the cost saving may not be as much as you think it is to go through this process. So in some cases, the utilities have decided, in spite of the fact that refurbishment is a less costly option, they felt that the risk from a management point of view overrode that economic analysis, and they decided to eventually go ahead with a greenfield option, in other words, replace all the equipment. So this is still a management prerogative, no matter what kind of assessment has been done. Thyristors. It does not appear to be a definite life for thyristors, subject to design and quality issues. So, for example, the Cobrasa scheme and Songo were replaced came in service in 1976, and they've been in service now for 40 years. We have done some testing on the thyristors at a company called Dynex in the UK, and the tests indicate that there is sufficient life left to maintain the equipment itself. Also, our Nelson River Bipole 2, the thyristors are some 38 years old and counting as well. So at this point in time, there isn't a lot of information available, but there doesn't appear to be any correlation. We also did another project to try and correlate some of the parameters that were starting to degrade with the actual thyristor failures themselves, and there didn't really seem to be any correlation between these parameters and the actual failures that we were seeing. So at this point in time, the life of these thyristors is kind of still an unknown. It appears at this point in time that it's at least 40 years. Usually the OEM will stop supplying these thyristors after about 20, say 25 years. So spares become a large issue, and of course they can become fairly costly as well. So at some point in time, you're going to have to decide, when there's a last time to order, how many you want to order to try and survive the predicted life of the equipment, and based on the thyristor failure rate that you're seeing, and maybe a bit of a higher thyristor failure rate for down the road. However, in talking to some of the thyristor manufacturers, they have offered to custom supply some of these thyristors. At this point in time, we haven't taken them up on that offer to see what is involved and what the cost would be, but we have purchased some off-the-shelf replacements from some suppliers. So for our Bipole 2, we have found the source as an example for off-the-shelf thyristors, so as far as replacing them and having a spare supply, that hasn't become an issue. Other things, cooling pipes, leaks, plugging, Grating electrodes, fouling are concerns with many of the systems. The cooling pipes, manifolds, and fittings are generally made of PEX or another type of plastic, and will likely have a life less than 40 years of the valves itself. And so somewhere in the 25 to 30-year range would require, I think, a detailed evaluation of the remaining life, providing you haven't had a lot of failures prior to that. Looking for cracks, thinning, connectors, deposits, and leak history is a significant portion of the work. Again, you can usually get some plastic suppliers and/or the OEM can generally supply replacements. Most schemes that I'm aware of that has wanted to get replacements from either the supplier or from a plastic supplier have been able to do that. So I haven't heard of anybody that's had a problem in doing that yet. The reactor modules, they limit the I/T across the thyristors so they don't fail, and help with the commutation performance of the valves. Plugging of them, overheating, and the iron cores, red dust are common causes. There are a number of cores in the reactor modules which saturate at different levels with current, and basically these are glued together with a glue, and generally over time and vibration, sometimes this glue tends to let go, causing a very, very fine iron dust, red dust in the valve itself, which during the inspections can be very easily looked for. And of course the units have to be taken out and then replaced because they can't be fixed usually. If of course there was to happen to be a water leak, you may actually have some problems with a flashover. But flow testing and ducting of connections, regular inspections, probably use of temperature strips if there's a thought that there might be some overheating, can give you a better idea of what's going on with the reactor modules. So again, OEM can supply for about 20 years, but can custom supply after that. So I already talked a bit about the supply of those 25 spares. Additional spares can extend the life, and they have in the case of our bipole too. The damping circuit limits the VBIT across the thyristors and also can be used to supply power to the valve electronics. The resistor may be water-cooled, so plugging and overheating can be similar to that of the reactor modules. Theoretically, they should last for 40 years with no design or quality issues, and we've seen this basically in our scheme in particular. Capacitors for damping and voltage grading may be oil-filled and may represent a fire hazard. They also have a lifetime of around 40 years. Replacements can be gas-filled, so you can, when you're going to a replacement, you can eliminate some of the fire hazard. The valve-based electronics provides communications to the thyristor valves for firing and monitoring of the performance and failures of the thyristors or the monitoring circuits. Fiber optics provide isolation from ground potential to the high voltage associated with the thyristor valves. Generally, a limited number of spares are purchased, and this can technically limit the life of the VBE if you start to have a number of failures with the spares. Replacements can usually be found for the VBE parts from the OEM or others, including the fiber optics, but generally these replacement parts will be quite expensive. Analog VBE parts can be still sourced and can have a life of 40 years or more. in both cases, our bipole 1 and bipole 2 are over 40 or approaching 40, although our bipole 1 has been replaced. Digital VBE, though, from the OEM would have a shorter life, and it's not clear whether or not you'll be able to get these parts much beyond 12 to 15 years. So likely that they would have to be replaced. Hopefully that at that point in time there is still parts available from the supplier. Fiber optics, failure of the protective outer jacket is the most common, as well as the connector itself and, of course, the electronics associated with converting the fiber to electronics and electronic to fiber. These are things, again, that generally you can find parts for, and you can still get replacement fibers. One of the real challenges is cleaning of the fiber optic channel. Because generally speaking, most valve designs are not designed to be able to clean this area. And if moisture should get into this area, a flashover will very likely occur. We've had that happen on a couple of times in our bipole 2 valves, where we've had a water leak, got into the fiber channel. We haven't gone in to try and clean the fiber channel because we also have a problem with the outer jacket failing, and we feel that we can actually cause more problems than failures. So we're just buying spare fiber optic cables and replacing them as necessary. Valve arresters are similar to other DC arresters. It should have a 40-year life, subject to design and quality issues and number of operations. They're likely available that you can get spare arresters. In a zinc oxide arrestor, of course, you can measure the current leakage rate as well to determine the health of the arrestor itself. For a gapped arrestor, you would have to remove from service and do a high voltage testing, and a minimum of 2 units is required to determine the health of the arrestors. Regular inspections for broken sheds, cracked discs, and other things as accessible. Valve support and bus standoff insulators are subject to intense vibrations due to the valve reactors. Grout failures, cracking of the standoff insulators are areas of concern, but most should last in the neighborhood of 40 years. Spares are really not an issue, as there are many potential suppliers. Fire design. Many of the older valves do not have fire as a consideration in the design. Fire barriers are required to reduce the chimney effect, as well as using self-extinguishing materials were not considered in the past. It was originally thought that valves would not burn, but after several valve fire failures throughout the world, this thought process changed. So you need to consider, as part of the life extension assessment when replacing the parts, if fire barriers can be added or retrofitted. We actually did this in our bipole 1 thyristor valves. We actually added in some fire barriers to reduce the chimney effect. Evaluation, setup criteria as per the above with weightings and numbers for good or bad. Weightings will depend on the criticality of the part causing the problem and the probability of obtaining replacement parts. It may be significantly different from link to link because each of the supplier's valves are fairly unique in the materials that they use and the way they put the design together. So it may be that you want to actually have a separate weighting evaluation criteria depending on who the supplier is. So it's a little bit harder to have a commonality here. Environmental issues. Environmental issues are the same as any other project, but the number of issues, scope, and costs may be greater because the size of HVDC converter stations. Items to consider such as asbestos, PCBs, or polychlorinated biphenyls, oil spills, glycols all need to be considered. So you may have to go through an environmental review process as an example. There also may be regulatory issues that you have to go through, whether major refurbishment or replacement. There may be licenses and different hurdles that you have to get approvals for at various levels of local, state, or federal government requirements. the cost of these environmental and regulatory um, compliances need to be included into the techno-economic evaluation. Techno-economic evaluation can be some of the most toughest part of the process to try and justify with a business case analysis. It's likely that you will need to involve some financial specialists to help you with this. Banks may be required to have, and also even the utilities or owner may require specific financial models that you have to fit the information into. Determining the discount rate, which is the interest minus inflation, is probably one of the most influential parts of an economic evaluation. This may be dictated to you by the financial organization or the owner or whatever, or it may be variable that you can consider this. And of course, the reversion period is also something that can be quite variable. Refurbishments are generally in the neighborhood of 15 to 20 years versus a new scheme, which can be 35, 40 years. So you have to make sure that you're comparing apples and apples as far as time frames are concerned. And the discount rate can dramatically affect the outcome of this process. So if you change the interest rate, you can be able to justify it, or you've changed the interest rate differently, you may not be able to. And similar with the refurbishment period. So I think it's a good idea to try and get and set these at the beginning of the analysis process so that you don't try and influence the outcome of the process, although in some cases the client may want you to help justify something. Difficulty in determining the cost of forced and scheduled outages and increasing reliability and unavailability. It is sometimes difficult to come up with average costs for forced and scheduled outages, but these are really important to do a business case analysis. Also, the unreliability and unavailability today will increase in the future, and of course some guesstimate or estimate has to be done as to what these unreliability and unavailability figures were, and probably you'll have to do some kind of a sensitivity analysis with respect to these to show that they're not overly optimistic or overly pessimistic and things like that. And so by going through these and determining these, you can come up with a business case analysis. You may need to consult other people, such as power sales marketers, to actually get a better idea of the costs of outages and things like that. And you may have to work with them to actually come up with the costs, because they may understand the costs, but they may not always understand the consequences of not having the HVDC equipment in service. In summary, a good maintenance program, such as reliability-centered maintenance, is essential to keep the equipment in good condition for extension and provide good records for review. A root cause analysis process is essential to maintain a high reliability and provide detailed information on the actual cause of the outage for a cost-effective life extension. So you're actually, and root cause analysis is actually finding the actual root cause and maybe not, so you're not solving a problem that isn't there. So you actually solve the problem that is the cause of the failures. It is essential to have a highly knowledgeable team of specialists with expertise in the key areas, as some life extension projects have not had a good outcome, with the improvements to reliability, availability, and maintainability as not as effective as what is possible. It is desirable also to do the lessons learned a few years after the life extension to see what worked well and see what could be improved. This is rarely, if ever, done, but if you're continuing to do these types of processes, it would be useful to learn what you did well and what didn't go so well, so things can be improved for further analysis on life extension. There are a couple of really good references for this, with a lot more information than what I presented in this webinar. And if you can gain access to these references, they would be extremely useful. First one is the Seeger Working Group B454, which is Technical Brochure 649. Guidelines for the Life Extension of HVDC Systems, published this year in February 2016, and I was the convener of that working group. And the other one is EPRI P162001, Life Extension of Existing HVDC Systems, and of course people from the Research Center, including myself, were contributors to that document as well. Thank you. Questions? The first question is, what test results to indicate thyristor life left? What we did is we partnered with a company called Hydro-Quebec and ourselves and a number of people in the HVDC users group. We got information from them that would do tests on thyristors of various parameters that were deteriorating. So we compared the thyristor parameters when they were first installed in a DC link, and then many years afterwards to see which parameters had changed, increased or decreased in value depending on which way they were going. And we tried to correlate then when the thyristors failed whether one of these parameters was the cause of the failure. And we could find no correlation between the deterioration of these parameters and the actual failures themselves. As far as the tests that we did on transformer life or thyristor life, the original thyristors that were supplied at the Cabora-Bassa link, as an example, were not thought to be able to stand very high fault levels for very long periods of time. And so they had what they call an overcurrent diverter, which would short circuit the converter transformers to protect the thyristor valves. However, this was not good for the converter transformers. So we did some tests with respect to thyristors of introducing 3 to 4 loops of fault current on the thyristor, and to see whether they would withstand those fault levels without any failures. And basically, these were extreme tests in that we're talking about faults in the neighborhood of initial fault current levels in the neighborhood of 19 to 20,000 amps, with an average in the neighborhood of about 15,000 amps for 4 loops of current. And we were able to actually remove the overcurrent diverters and put in a high-speed tripping circuit that would trip the thyristor valves in 2 loops of current, similar to what we have in our bipole 2. I also talked to the original designer of the thyristors themselves, Chandra Krishnaya, and basically got a lot of information from him on tests that they had done in the factory that they had, of course, never released, and found out that these thyristors had a significantly higher fault capability than what they had originally supplied, and of course had to guarantee. So even though that they had a higher level, because they had to guarantee these thyristors, the guaranteed level is much less than what the actual capabilities of thyristors are. So based on actual failures and correlation to degrading components or parts of the thyristors, testing at Dynex at a severe level, and discussions with the original designers of the valves at Cabora-Bassa and at Nelson River, and I guess some other links in the world, came to the conclusion that it's very likely that these have a much longer life than the 40 years. I indicated in the controls for the transformers that the life of the components is about 30 years. This is talking about relays and those types of components. It's not talking about more modern day controls, which would be software based. The software based controls or digital controls we call them, for lack of a better word, generally have a life of 12 to 15 years. Suppliers will tell you it's longer, and we have evidence that in some cases it's even shorter. So what I was talking about there is many of the transformers that you're doing the life assessment on at this stage are in the neighborhood of 25 to 30 years old. They are still the old relay type components and things like that. So mechanical type components. So there is a huge difference between what we call analog controls, and these would be classified as analog controls, and basically the more modern day digital controls. Definitely the digital controls will have a limited lifetime, and you can pretty well say that as soon as you build a DC link, if you have digital controls, 12, 15 years down the road, you should almost automatically put in a placeholder to have a capital project to replace your controls. Okay, thank you for joining the webinar. If you have any other questions, please email us at info@hvdc.ca. Thanks again.